Alright, hello guys. I'm gonna. So, this is a juicy article. I had been waiting for this article for long. The reason why it's juicy is because uh, the half of the keywords in this article I have no clue what they are. So, it will be probably it'll be a juicy video as well, right? So, let's dive in. Now that we have some more types under our belts, turns out we can give these types some additional attributes that control their behavior. These are the type qualifiers and storage class specifiers. Type qualifiers. These are going to allow you to declare constant values and also to give the compiler optimization hints that you can use. Const. This is the most common type qualifier you will see. It means the variable is constant and any attempt to modify it will result in a very angry compiler. See, is new I.H. I do want to. I have 3 more articles to go in this before I develop a good project in C to really firm or really make the knowledge I make the the stuff I've studied from these articles I could really concrete it. Is that how you say it? Concrete it, not concrete it. To really structure it and don't make it let go of my. What the fuck am I saying? I think moments like this, you just have to stay silent and just recollect in your brain what you want to say. Yeah, I don't have any idea for a project. Const. Yeah, you can't change a const value. Compiler puking sounds can't assign to a constant. Often you see constant parameter lists for functions. Void foo const int x print f x plus 10. Okay, doesn't modify x. Okay, so you see constant pointers. This one gets a little funky because there are 2 usages that have 2 meanings when it comes to pointers. For one thing, we can make it so you can't change the thing the pointer points to. You do this by putting the const up front with the type name before the asterisk in the type declaration. Oh, okay. Int x of all. Yeah. If you don't want to mutate the value the pointer is pointing to, then put the const declaration before the type name. We can modify p, no problem, but we cannot do that. Somewhat confusingly, these 2 things are equivalent. What the fuck? Great. So we can't change the thing the pointer points to, but we can change the pointer itself. What if we want the other way around? We want to be able to change what the pointer points to, but not the pointer itself. Just move the const after the asterisk in the declaration. Oh, we can't modify p with the pointer arithmetic, but we can modify what they point to. You can also make both things constant. Oh, hell yeah. Okay, so this is kind of confusing for me, at least. I mean, I haven't tried this in code, but yeah, I mean, why would they? Yeah, look, somewhat confusingly, why would they put both of them together? Why would they make both of those sentences or both of those statements the same meaning? I wonder if there's any history behind this, of why const is before the type declaration and const is before the type and const is also after the type. I wonder, is there any like history or relevance to it? Great. So we can't change the pointer. Yeah. So, how do we change? How do you not change the value inside the pointer? I mean, no. How do you change the value? How do you not change the pointer, but you can change the value of the pointer? You write const, not const. You write int, asterisk, const, and pointer. There you go. But we can modify what they point to. That's good. You can also make both things constant. That means modify the pointer itself and the value the pointer is pointing to. Finally, if you have multiple levels of indirection, you should const the appropriate levels. Just because a pointer is const doesn't mean the pointer it points to must also be. You can expressly set them like the following: car star star p. That means the pointer is alright, the pointer is pointing to the pointer P. No, the pointer P is pointing to is alright. It's mutatable. Is it mutatable or mutable? Mutable. And the value that the value pointed by the pointer pointed by the P pointer can also be mutated. There you go. P plus plus, that is the pointer itself, and then wait, is that asterisk? Then means that's this pointer. Yeah. This pointer. Wait, how do I read this? Let me see. So P plus plus is that pointer is there, and the value is there. Pointer P plus plus would mean this pointer is being changed. P star would mean get this guy and this change this guy. Yeah. And the value would be P star, right. So in order for me to test that hypothesis, let's do car star P, right? Now I do need, okay, so what my idea is, it's like this, star P. What the fuck? Oh, that was cool. What did I do there? Right? So this should, I'm going to put N because I love the letter N, and printf C, and what I'm going to do is put not P star P. Is this the same as indirection 2 times? Let's see if it's the same as indirection 2 times. Segmentation fault, makes sense. So what I'm going to do is I'm going to write not this, do this. Oh my god. Right. Segmentation fault again. Okay, why is it an segmentation fault? Character, boom. This thing brings out a pointer, and this brings out a pointer as well, right? Then why doesn't it do that? No, that's a pointer to pointer. If I do that, this is what will happen. Okay, let's just not do character int, right? And then I'm going to do 0. Oh my god, D. Segmentation default. Okay, now I don't know why segmentation fault is coming. Let's do 1 first. Right, star P 0, and then I'm going to do this. What the fuck? Why is it still like this? Am I doing something wrong? Printf studio.h int star P equals 0. Okay. Obviously I can't do it this way. Sorry about that, guys. Main.c. Yeah, makes sense. Then why the fuck are you not working? Star P equals. Obviously this is not. This is wrong as well. What the fuck? Okay, that is wrong. Okay, I'm gonna put P because that's how you show. What the hell is happening, guys? What the hell is happening? I am printing. Oh wait, no. P. What the fuck? You know what? I'm gonna do this then. X equals 0. X equals, not X equals, P is equal to and X, and then now show me the. Yeah, that makes sense. I believe that's the pointer address of P. I mean not P, of P, X. Now I'm gonna put some other number, 9 0x9. Wait, because yeah, replace D 9. There you go. Now why the hell is this not okay? Is that the reason why? Because the thing was not instantiated. Is that the reason why? Okay, cool. Okay, cool. I guess. Now what do I do though? Okay, I need this as an example. Star P, boom boom, and then int x equals 9. Int star P equals a what the fuck x, and yeah, not P. I'm going to write Q, and Q is equal to and Q as well. Right now I believe it should work. Printf the double on what the double asterisk should work. Okay, and let's see. Nine. There you go. That good. Okay, probably why that didn't work is I'm not gonna look it up. Probably the why that asterisk P did not work was it was not instantiated, and I did it directly, most likely. Okay, now I'm gonna look it up. Okay. Yes, ask Cloud. I'm gonna ask Cloud. Cloud. Why do I keep on saying it as Cloud? It's Claude. It's Claude. You know, it looks like Cloud, bro. That's why. Probably. I mean, the E and the A is there, but yeah. Claude. Anyways. I'm not gonna do that. Int star P equals what the fuck? No, shit. I'm treating it as if it's Vim. Equals 4. Does this work? Okay, what is this pointer arithmetic? No, that's pointer arithmetic, gang. I don't need that. I want to ask Claude. Sorry, Claude. Is because I think no, not I think. I was embarrassed today. I was talking with my mentor, and I mentioned I used Cloud, right? Print f and boom. D. Don't hallucinate, right? And I said Cloud, and he was like, what the fuck is Cloud? Not what the fuck, but I'm paraphrasing there. I was like, oh, sorry, Claude. It was a bit embarrassing. And that too, right after I was not getting one of the assignments he was saying, and he like dumbed down the assignment to another type of assignment, which is it's not same, but yeah. Oh my god, it's taking so long. My net's fucked. Oof. A bit longer. Thanks for your patience. Man, I'm gonna do ChatGPT this shit, bro. I can't wait this long. I have juicy content to go through. ChatGPT. Come on, there you go. Oh, there you go. Oh, there you go. I like how yeah. Since P doesn't point and evaluate the first derivative itself is when this is causeless segmentation other than the defined behavior. Yep, there you go. There you fucking go. So what I predicted was the problem. It was not initialized properly. Nice. Okay, I think I wrote equal to sign. Okay, no. Okay, let's go this way, and yeah. So character star star as P. Now, what this means? Oh, I'm gonna guess what this means. I mean, I saw the answer, but I still say asterisk. That means if the const is outside, that means the pointer will not change. That's what it means. No, the value inside the value at the end of the pointer will not change. That's what const there would mean, right? But this would mean star const means, I saw the answer. It meant that the first pointer, like we have pointer to value. This pointer, if you modify, no, the compiler will be puking all over you. Yeah, there you go. And then that pointer is all right. Next, okay, it's character star const star p. I mean, you could guess that goes. The pointer. You can't modify this little shit. The second in between model. There you go. And star pointer value. You can't modify any of those two pointers. And if you put const before the type declaration, you can't modify the value as well. Const correctness. One more thing I have to mention is that the compiler will warn on something like this: const int x equals 20, int star p equals and x. Say something to the effect of initialization discards const kernel fiber from pointer type target. What's happening? Well, we need to look at the types on either side of the assignment. Const int x equals 20 and int star p is equal to const int star. The compiler is warning us that the value on the right side of the assignment is const, but the one on the left is not, and the compiler is letting us know that it is discarding the constness of the expression on the right. This is, we can still try to do the following, but it's just wrong. The compiler will warn and it's undefined behavior. We can still try to do the following, but it's just wrong. The compiler will warn and it's undefined behavior. Oh, so we don't know what it will get. Modifies x, maybe not. Okay, 40 if you're lucky. Oh, okay. Nice. Restrict. TLDR, you never have to use this and you can ignore it every time you see it. If you use it correctly, you will likely realize some performance gain. If you use it incorrectly, you will realize undefined behavior. Restrict is a hint to the compiler that a particular piece of memory will only be accessed by one pointer and never another. That is, there will be no aliasing of the particular object the restrict pointer points to. If a developer declares a pointer to be restricted and then accesses the object it points to in another way, example via another pointer, the behavior is undefined. Basically, you are telling C, hey, I guarantee that this one single pointer is the only way I access this memory, and if I'm lying, you can pull undefined behavior of me. Why undefined behavior? I wonder what's the history behind that as well. There is, every time some type of decision making is there, like some type of design issues, and I don't know whether this is a design issue. I feel like this is a design issue from what I've coded before, but I am not very well versed in C, so don't quote me on that. I am interested on the history behind that undefined behavior for this and maybe other undefined behaviors. Instead of making it an undefined behavior, I speak too fast. Instead of making an undefined behavior, why didn't they have it as an error? Right? Why was not that the case? I wonder what the history behind that would be. Basically, you are telling C, yeah, and C uses that information to perform certain optimizations. For instance, if you dereference the restrict pointer repeatedly in a loop, C might decide to cache the result in a register and only store the final result once the loop completes. If any other pointer referred to that same memory and accessed in the loop, the results will not be accurate. Note that restrict has no effect if the object pointed to is never written to. Oh, it's all about optimization surrounding writes to memory. Okay, so it has no effect if the object pointed to is never written to. Let's write a function to swap two variables. Oh, okay, nice. Okay, void swap int s restrict. Ooh, fancy. Int asterisk restrict b. Int t is equal to star a is equal to star b, and then star b equals t, t, int x equals 10, y equals 20, swap and x and y, swap and x and x. That's going to be undefined behavior. Okay, a and b above point to different things, so it's not restricted movement, but it doesn't unrestrict the movement. It doesn't disobey the restricted movement of the pointers, but this is undefined behavior because a and b point to the same thing. If you had to take out, okay, I'm gonna wait. D x equals d y equals d and nope. X and y, boom, and yada yada. See this shit. Yeah. What I'm expected to see is if swaps work x and y, yx will become 20, y will be 10. So 20 and 10. And here it will be just 20 and 20. That's what I expect, but doing that, going about it in an unrestricted way for a restricted pointer will give you undefined behavior. There you go, it's undefined behavior. The first x is 20, but yeah. If you take out the restrict keywords above, that would allow both calls to work safely, but then the compiler might not be able to optimize. Restrict has block scope, that is, the restriction only lasts for the scope it's used. If it's in a parameter list for a function, it's in the block scope of that function. If the restricted pointer points to an array, it only applies to the individual objects in the array. Other pointers could read and write from the array as long as they didn't read or write any of the same elements as the restricted one. Oh, it applies to the individual blocks. If it's outside any function in file scope, the restriction covers the entire program. Okay, you are likely to see this in library functions like printf. Again, that's just telling compiler that inside the printf function, there will be only one pointer that refers to any part of that format string. One last note, if you're using array notation in your function parameter for some reason instead of pointer rotation, you can use restrict like so, with no size, restrict with size, but pointer notation will be more common. Why is this a thing? I don't know. If the restrictor pointer points to an array, it only applies to the individual objects in the array. Individual objects. Other pointers could read and write from the array as long as they didn't read or write any of the same elements as the restricted one. So does that mean sorry about that, does that mean the restrictor pointer points to an array, it only applies to the individual objects in the array? So does that mean like whoever, so every time the pointer points to the first element in the array, right? So if you use another pointer to access that, right, because this is different because you are you're using x in different ways. Oh my god, I forgot what restriction is. Oh yeah, okay, yeah, because yeah, makes sense. Yeah, you can't refer to that memory, you can't refer to that memory. So yeah, makes sense. Let's go down. Yeah, that's what I mean. If other points could read and write from the memory as long as they didn't read any of the elements as a restricted one. I believe that's what it means. ChatGPT board. Nope, you're not going to see my search results. I really need to off the search results, but but sometimes I close tabs accidentally, and only the search results helps me in keeping it. What's keeping it? Only the search results help me not lose that tab. What does this mean in the context of C? Oh my god, the internet sucks, bro. Oh my god. Oh my god, this thing takes so much time. You know what? I'm not gonna do it. I'm not gonna use ChatGPT. I'm just gonna use it. I'm just gonna see if it works, right? So my assumption was that I should have did that. Okay, let's just say it returns. It is a looping motherfucker. Okay, if you do that, it's undefined behavior. So I think I need to point that out. I'm going to void and loop array, right? And what he meant was, if you use restricted pointer points to an array, right? So let me see int p restrict, right? For int I is equal to 0 and I is less than 10, I plus plus, boom, printf d p, and that is accessing it. Okay, p0. Okay, now yada do this. What I'm going to do is int star h is equal to p, and that is going to give me the value of it, p plus, not p itself, and then what I'm going to do is dereference h. Now let me see if this works or not. Int p equals 1 2 3 4 5 6 7 8 9 and 10, right? And yep, and do this as well, and then loop array, put just p in there, and let's see if it works. It became 1 1 1. Oh wait, okay, so it has no problemo. Huh. See what I mean? I don't think I understood what the fuck he meant. I really need to use this. I don't care about your thinking, guy. Okay, it's thinking a lot. The statement is correct. In C, the restrict qualifier applies to the entire object that the pointer points to, not to individual elements of an array. If a restricted pointer points to an array, the entire array object is considered to be accessed solely through that pointer or pointer derived from. Any other pointer that is not based on the restricted pointer, that is not derived via pointer arithmetic or aliasing from it, cannot legally access any element of that array, even a different element, without causing undefined behavior. The standard explicitly states that if a pointer q not based on p is used to access the object p points to, the behavior is undefined and the object is the whole array. Note its thus pointer. Oh, okay. So they are saying that he is wrong. I don't know what's the answer to that question, because I haven't read the the documentation by myself. If you guys have an answer, do put it in the comments down below. You are likely to see yeah. Okay, and what is this done? I guess this means the same thing as well. Yeah. Volatile. You are likely to. Oh wait, what does this mean then? Ooh. I don't really give a shit if you see me. What about this? In both of these forms, the strict qualifier approach to the pointer that is from the pointer to take it. Their size or lack thereof does not change the semantics of strict. It still means the dimension reachable to that pointer. Okay. Volatile. You are unlikely to see or need this unless you are dealing with hardware directly. I might need this. Volatile tells the compiler that a value might change behind its back and should be looked up every time. An example might be where the compiler is looking in memory at an address that continuously updates behind the scenes, example some kind of hardware timer. If the compiler decides to optimize that and store that value in a register for a protracted time, the value in memory will update and won't be reflected in the register. By declaring something volatile, you are telling the compiler, hey, the thing this points at might change at any time for reasons outside this program code. Volatile in *p. This is an optional C feature that we'll talk about in the atomics chapter. Storage class specifiers. Storage class specifiers, similar to type quantifiers, they give the compiler more information about the type of a variable. Auto. You barely ever see this keyword since auto is the default for block scope variables. It's implied these are the same. The auto keyword indicates that this object has automatic storage duration. Is that in the scope? That is, it exists in the scope in which it is defined and is automatically deallocated when the scope is exited. One gotcha about automatic variables is that their value is indeterminate until you explicitly initialize them. We say they are full of random or garbage data, though neither of these really makes me happy. In any case, you won't know what's in it unless you initialize it. Always initialize all automatic variables before use. Static. This keyword has two meanings depending on if the variable is file scope or block scope. Let's start with block scope. Static in block scope. In this case, we are basically saying I just want a single instance of this variable to exist shared between calls. That is its value will persist between calls. Static in block scope with an initializer will only be initialized one time on program startup, not each time the function is called. Let's do one example. Static in count equals 1. This is initialized one time. Printf, this has been called this many times. That's cool. So that's what static does. Static with an initializer will only be initialized one time on program static, and they can be shared between calls. It's just one instance of this. See how the value of persists between calls. One thing of note is that static block scope variables are initialized to 0 by default. Default starting to 0, so the assignment is redundant. Finally, be advised that if you are writing multi-threaded programs, you have to be sure you don't let multiple threads trample the same variable. Static in file scope. When you get out to file scope, outside any blocks, the meaning rather changes. Variables at file scope already persist between function calls, so that behavior is already there. Instead, what static means in this context is that this variable isn't visible outside of this particular source file, kind of like global, but only in this file. More on that section about building with multiple source files. So more on that in the section about building multiple source files. So I'm not gonna try to understand what he means by this. You know what? I still do it. Instead, what static means in this context is that this variable isn't visible outside of this particular source file. So it's like private, I guess. This is a bad example, kind of like global, but only in this file. The extern storage class specifier gives us a way to refer to objects in other source files. Let's say, for example, the file bar.c had the following as its entirety. Just that, declaring a new int in file scope. But what if we had another source file foo.c and we wanted to refer to that in to the a that's in bar.c? It's easy with the extern keyword. We could also have made the extern int in block scope and it still would be have referred to the a in bar.c. Now, if a in bar.c had been marked static, this wouldn't have worked. Static variables at file scope are not visible outside that file. A final note about extern on functions. For functions, extern is the default. Okay. So it's redundant. You can declare a function static if only you want it visible in a single source file. Register. This I read in from Speak Machine. he was talking about his code, his source code for the spell checker. So yeah, what it does is it stores your variable in a register. This is the key way to hint the compiler that this variable is recurrently used and should be made as fast as possible to access. The compiler is under no obligation to agree to it. This is the thing. What the fuck? The compiler is under no obligation to agree to it. Now, modern C compiler optimizers are pretty effective at figuring this out themselves, so it's very rare to see these days. But if you must, it does come at a price. However, you can't take the address of a register. Oh, the same applies to any part of an array. Oh. Rambutan. Hi, my mom just came in to bring me mango slices and 2 rambutans as well. So I'll be eating this while reading. So yeah, the same applies to any part of an array. Register int a, and you cannot take the address of a0. Dereferencing is not also applicable. Interesting. The fuck. So you can array notate, but it will warn you. ISOC forbids subscripting register array. The fact that you can't take the address of a register variable frees the compiler up to make optimization around that assumption if it hasn't figured out already. Also, adding register to a const variable prevents one from accidentally passing its pointer to another function that will fully ignore its constness. Oh, nice. Also, a bit of historic backstory. Here, deep inside the CPU are little dedicated variables called registers. They are super fast to access compared to the RAM, so using them gets you a speed boost. But they are not in RAM, so they don't have an associated memory address, which is why you can't take the address of or get a pointer to them. But like I said, modern compilers are really good at producing optimal code using registers whenever possible, regardless of whether or not you specify that it's a keyword. Not only that, but the spec allows them to just treat it as view typed auto if they want, so no guarantees. Thread local. When you're using multiple threads and you have some variables in either global or static block scope, this is a way to make sure that each thread gets its own copy of the variable. This will help you avoid race conditions and thread stepping on each other's toes. If you're in block scope, you have to use this along with either extern or static. Also, if you include threads.h, you can use the rather more palatable thread local as an alias for the uglier thread local. Can be found in the thread section. So yeah, that is types 4 qualifiers and specifiers. So that was an interesting article. I learned a lot about keywords, and we are going to move on to another interesting part: multi-file projects. I have never done multi-file projects. I mean, like whenever I'm thought of C, is only like one file, at most 2, and they're not connected, they're just 2 separate programs, right? So this will also be interesting. And there's another one which I didn't really get, the outside environment. Oh, this is just probably just argc and argv. This will be very easy to go through. Next we have the C processor. This is a I think this is the biggest article commit to all based on the number of titles it has. So yeah, multi-file projects. See you next time. Bye.